Okay, good morning, everyone. I think this is where we left off with Hipparchus. We had looked at his other great accomplishments, reference systems to map the celestial sphere, the brightness scales of the magnitudes, which he gave us, his further work on the precession of the equinox and things like that. But here we have, he adds a geometric device, something else that Ptolemy is going to use in his bag of tricks. And it's called the eccentric point of an orbit or a path. Eccentric simply means it's off center. And he discovered this as he studied the path of the sun going around the earth. And he found that the sun seemed to travel at different speeds, that the fall and winter quarters were shorter than the spring and summer quarters. Now, of course, according to Plato, the sun moves at a constant speed. So Hipparchus was not free to go ahead and having the sun start moving at different speeds. So how else could he do this? He could do this by simply putting the earth off center. If you put the earth off center here, and this point is called the eccentric point, then as the sun comes around and is closer to us, it seems to move more quickly. And when it's far away, it seems to move more slowly. And so this very, very simple device of just simply moving the earth off center works very, very nicely for the sun. And Ptolemy keeps this completely for the sun. We have no need for any epicycles. We simply need to move the earth off center. Now, of course, this earth is still the center of the universe. All we're simply doing is taking the path of the sun and moving it off center from that center of the universe being the earth. So this is a very nice device that we will see are being used. However, this is a first step away from the cosmology of Plato and Aristotle by not having one of the planets, the sun, being its center, being the center of the earth. So this is definitely a step away that the mathematicians used to build a better model, to save the appearances. So philosophers will just have to accept it, that this does make better predictions for where the sun is in the sky. So let me show you how this works, how he came up with this. We have the 4 seasons, and like I say, they're not of the same duration. The fall and the winter are shorter than the spring and the summer. So Hipparchus had the idea, well, why don't we go with that? Why don't we put the earth right there in the crosshairs? So with the earth here, we will see a shorter fall and winter and a longer spring and summer because we're closer to the fall and winter and further away from the spring and summer. We now know that this is not only a good geometric idea, it's also correct. We know that we are closer to the sun during the winter than we are in the summer because of the tilt of the earth. Hipparchus came on this just because he wanted to get the seasons correct and had this idea of the eccentric point. He even can tell us how far away the eccentric point is from the center of the sun's orbit. And this is a very nice piece of geometry. Here's this angle that he can measure. He can measure on the fall equinox. He can measure the angle here that the sun is making on the ecliptic. If you call the distance of the path just 1, just to keep things simple, you notice that we have our very nice central proportion. We have theta is to 360, as this angle here is to, as this angle here, 89, is to 365. And this is how he measures the angle. Theta is to 360, as 89:365. And we can cross multiply and solve for this angle that the sun makes with the Earth and on the full ecliptic. But notice finally that the cosine of this angle, now that we have the angle, is the adjacent over the hypotenuse. The cosine of this angle is the adjacent over the hypotenuse, but the adjacent is EC. That's the offset. R is simply 1, so this offset is simply the cosine of 87.78, which is about 4%. So this offset is about 4% of the entire radius of the orbit of the sun. A very nice piece of work. Not only does he have the qualitative idea of moving the Earth off center, he can tell us quantitatively how far off center it is by measuring the seasons. Very, very nice. And let me show you the animation of this. So here we have the path of the sun. But Hipparchus is not happy with this path of us being in the center. It doesn't fit the length of the seasons. So he simply moves this Earth off center. Doesn't change the path of the sun, doesn't change its constant speed, as Plato insists, but he gets that change in seasons by simply moving the Earth. Very, very nicely done. And like I say, Ptolemy will use this for the sun itself as well. Why does this work so well, guys? When you put the Earth here, this path with respect to this green dot looks like an ellipse. It very much has the characteristics of a mathematical ellipse. And that, of course, is the right answer. The Earth does go around the sun as an ellipse with that offset of just about 4%. Of course, Hipparchus was not prepared to think about that. That was not in his mental furniture. He was working exclusively with circles, but he actually came up very nicely with the answer of an elliptical path from that point of view of that off center. And I mentioned that Apollonius's device is so powerful, so flexible. Let me show you how you can create this eccentric without even moving the sun, by literally moving the path. So here we have the wrong path of the sun going around the Earth because it's at an even circle with us in the middle. All we have to do is to create the right epicycle and difference. And now we have the sun going around on the blue path, exactly the same size path. It's just we now have moved the sun off center. So you see how powerful the idea, how flexible this idea of the different epicycle mechanism of Apollonius. What this shows is you really don't need the eccentric point of Hipparchus. You could just as well do these. You could do these when you want to have off centers. But certainly the eccentric point is much simpler conceptually.
Peter,
Yes.
it's not intuitive to me that orbits would be anything but circular. Is that
Yeah, it wasn't to anybody else until Kepler in the 1600s. It was one of the great revolutions in the history of thought. Break away from Plato's cosmology.
But what's the physics of it being non-circular? I mean, is it a difference in density in different parts of?
No, you know the answer to that. It's Newton's laws of motion and the law of gravity. Newton comes along with his 3 laws of motion and the law of gravity of the force, and you calculate what the orbits have to be using those physical laws, and you get ellipses. It's as simple as that. It is a mathematical consequence of Newton's laws of motion.
So the Earth and the Sun are uniform spheres. It's not anything to do with variations in the density of the two objects.
No.
Okay. Next year.
Yeah, exactly. Exactly. We'll be going through that next year.
Peter?
Yes.
So he was only dealing with the amount of time, the difference in the days.
Yes.
He wasn't dealing with the climate, like if the sun is closer to the earth in the winter, well, then why wouldn't it be hotter?
Right. Yeah. It was a bit of an anomaly to Hipparchus and the people of the day that was the case. It seemed strange, but the sun on the ecliptic and how it made its path going from equinox to solstice to equinox to solstice, these were very definite places in the sky that they could measure very, very accurately. And those were the numbers that they found, 89 for the two of them and 93 for the other two. So he just went with that to find his orbit. But it was a bit of an anomaly. It's still, many people still, if you ask the guy on the street, in the summertime, is the sun closer? Well, yeah, sun's closer, it's hotter. In fact, it's not because of the tilt of the Earth. Well, and again, just to show one more flexibility and power of the different epicycle system, it's very easy to make an ellipse. Nothing to it. Of course, the Greeks were not interested in this curve, so they never explored it in terms of the astronomy. Apollonius proved hundreds of theorems about these curves, ellipses, hyperbolas, and parabolas. He literally wrote the book on these curves, but no one applied them to the astronomy of the day, even though this would have been the perfect answer for the sun to go around the Earth, because in fact the Earth does go around the sun as an ellipse. This wouldn't have helped with anything else because the other planets going around the Earth, as we saw, are quite complex and are not elliptical going around the Earth. Okay, I think we're finished with. So this is the first usable model of the heavens that Hipparchus comes up with. It's not as complete as Ptolemy. Ptolemy comes up 250 years later. More work, more research, his ideas thrown in. But this is an example of Hipparchus's solution to the moon. The motion of the moon is very, very complicated. One reason is it's so close to us that we can tell its differences more easily. And what you have here is the eccentric point of the Earth. Yes, the moon's major difference is the Earth is made to be off-center. He makes an eccentric point for the moon. And what he does, he has this point. This point is the center of this difference. But this point is going to move. He has this point moving in a circle. So the whole difference is sloshing back and forth because its center is being carried around this smaller different circle. And then he finally has the epicycle where the moon's going around. The moon's epicycle sphere is being carried around by this moving difference sloshing back and forth. And this is not a bad solution to where the moon is in the sky. It does give very nice predictions of the position of the moon in the sky. The problem with this, as you can see, is that the moon is sometimes quite close to us and sometimes quite far away. With all the sloshing back and forth, you can imagine the moon being extremely close to us, somewhere around here, and extremely far away when this thing sloshes over here and the epicycle's up here could be very, very far away. The moon is so close to us, guys, that will make the moon look bigger or smaller in the sky. If the moon is that much closer to us, it'll literally look bigger in the sky, much bigger. And when it's that far away in the other extreme of Hipparchus's orbit, it'll look actually quite much smaller. But we don't get that kind of deviation of the moon. Moon does have a slight deviation in its elliptical orbit, but nothing that the eye could detect. Okay? You really need a telescope to detect that well. This could be easily detected. So this is a great weakness in Hipparchus's model. Kind of goes back to Eudoxus. Eudoxus solved the problem of the position of the planets in the sky, but he did not get the brightnesses correctly or those relative distances. Hipparchus does the same thing. He can get a much better view, much better model of the position of the moon in the sky. The center of the moon is located quite accurately at any time, but it's blowing up and shrinking like a balloon. And that clearly is not what happens physically. So this is only a half a solution. Something here has got to, we need more improvements on this. But to see the device that Hipparchus goes through using this kind of geometry to do this. The last thing I have for you is his measurement of the distance to the moon. And this is quite wonderful. He uses a lunar eclipse. I'm sorry, he uses a solar eclipse where the moon gets in the way of the sun. And he uses, for the first time in the history of astronomy, parallax. He views this eclipse from two different places on the Earth. He has his fellow astronomers working in another observatory to coordinate the observation of this solar eclipse. You know that in a solar eclipse, there'll be a small path, which is called the path of totality. If you're lucky enough to be along this path, the sun is completely blocked out by the moon. But as you go away from that path, only part of the sun is blocked out, and even less is blocked out, and even less is blocked out as you move away from the path of totality. So here we have the solar eclipse. We have the moon getting in the way of the sun. Here in Alexandria, we're at the path of totality. The moon exactly blocks out the sun. Up here in this city here, marked B, Thessalonic, which he knows is 470 miles away. This distance here is 470 miles. He knows that his astronomers report to him that what they see is 1/5 of the sun, that 4/5 of it is blocked out, and they only see the top 1/5 of the sun. Well, if we know that this angle is a half a degree, this is well known to us. The size of the sun in the sky, I'm sorry, the size of the moon and the sun in the sky is a half a degree. If this thing here is 1/5 of the whole thing, then this must be 1/10 of a degree. So he now knows that this angle that they see it be of the amount of the sun that they can see is 1/5 of the degree. And now watch, guys. These two rays coming in from the edge of the sun are parallel. This blue ray comes into B and the black ray comes into A. These two rays are virtually parallel, a la Eratosthenes, for the same reason. You say, well, how can they be parallel? They meet here. They're clearly not parallel. Yeah, but this is 470 miles. This is 93 million miles. These two rays are virtually parallel. We cannot, with our modern technology, detect the difference in these two rays going off to the same place, because this distance is only 470 miles. This is nothing compared to where they meet. And remember, all these pictures of astronomy are ridiculously not to scale. So if these two rays, this blue ray coming from C and the black ray coming from C, are parallel, then look at this line of sight here from B to M. As we see the edge of the moon, the ray that we see at B at the edge of the moon is a transversal of these two parallel lines. BM is a transversal of these two parallel lines, and therefore alternate interior angles. We have alternate interior angles, and this angle way up here at the moon, he's measuring the angle at the moon. Aristophanes is measuring the angle inside the center of the Earth. Hipparchus is now measuring an angle up at the moon because of the geometry. So if this angle is 100, this angle is a tenth of a degree, this angle is a tenth of a degree, and my goodness, don't we have the skinny triangle approximation all set up? This is a tenth of a degree. So a tenth is to 360, as 470 is to 2 pi, the distance to the moon. Okay. 1/10 is to 360, as d, the straight line distance, is to 2 pi, distance of the moon, right? The circle that this thing is on. We cross multiply, and of course he can write any distances. He first of all calculates a distance, but he can turn that into distances of the Earth, diameters of the Earth, because he has the Earth from Aristophanes, and he sees that the distance to the moon is 34 Earth diameters by his little calculation. We know that the modern value is about 30. But what's more interesting is he improves Aristarchus. Aristarchus, remember, had 38.2 Earth diameters. Hipparchus gets it down to 34. A nice achievement here in accuracy. A very, very nice piece of geometry. Questions on this? Don't let me snow you on this. Questions? This is not a simple argument if you're not used to looking at geometric arguments. Questions or comments? Okay. And so, you know, astronomers know their history and they love their history. I think more than any other discipline that I know of, science discipline, astronomers love their history and celebrate their history. So when it came to make the first mission, space mission, to measure distances to the sun, to the stars by parallax, they called it the Hipparchus mission. It's a mnemonic for, do I have the mnemonic here? I'm not sure. Yes, I do. High precision parallax collecting satellite. They like to put these torches in because they want to celebrate Hipparchus, who was the first astronomer in history to ever use parallax. This, of course, is a classic use of parallax. We have the Earth going around the sun with a very, very long baseline, not 470 miles, but now 93 million miles going back and forth. And if we could measure this angle P from seeing two different places in January and July, seeing this angle, we of course have the skinny triangle approximation. P will be to 360 as 1 AU, 93 million is to 2 pi d, d being the distance to the star. Okay? And this is was the first mission to do this using a satellite mission. And this was the orbit even that they used. They used a very, very eccentric orbit. The perigee, the closest to the Earth, was 310 miles, but the furthest was 22,000 miles. Why? Well, it goes around the Earth in 11 hours, very, very quickly. So when you're over here and you wait for this out here, you get an extra 22,000 miles of baseline. And over here, if you wait until it gets out to that far part of the orbit, you get another extra 22,000 miles. And every decimal point counts to get the widest baseline possible. So they set this orbit to be highly eccentric for science reasons, but also a nod towards Hipparchus. And like I say, our last slide here for the day. astronomers love their history and they know their history. And here's just, for example, the famous Jupiter mission the famous Galileo mission to Jupiter, and so many other missions are named after the great astronomers. All the great craters of the moon are named after astronomers and the Greek philosophers and all that stuff. Here's a monument up in observatory up in Los Angeles, in which they have the six great astronomers up through the 18th century. And of course, these names Copernicus, Galileo, Kepler, and Newton. Yeah, these are household names. But the other two that are added to the six sides is Hipparchus on one side and Herschel on the other. And Hipparchus certainly is not a name known as well as the other four, but now you do. Now you know them and his great accomplishment. And Herschel, again, is not a household name. Herschel is the person who discovered Uranus, among other things, the first planet discovered in historical times. He also revolutionized astronomy by his telescope design. He began making telescopes larger than anything ever done before, moving away from lenses and moving into mirrors. And the mirror design allows us to create much, much larger telescopes. And all the big telescopes today, and have been for many generations, are all mirrors coming from Herschel's basic design. And he did much, much more. He is the greatest astronomer of the 1700s. And so Hipparchus is in good company. Okay, any questions or comments before we go? I hope you enjoyed that couple of pieces of geometry. I hope I haven't went through it too fast.
No, it was interesting, and thank you so much for doing what you did today, not failing while I appreciate it.
Yeah.
Okay,